Before we dig into examples of Stokes' theorem, there are two things that we should really clear up. One is, what do we really mean by boundary of a surface? And then second, this compatible or positive orientation. So let's start with this boundary business first. Boundary of S. If the surface of S were made out of paper, then the boundary of S would consist of the edges. That is, the places where you could get a paper cut. So as an example, let's first just take a look at a sheet of paper itself. So this would be a surface. Yeah, and then the boundary for this surface would consist of all the places you could get a paper cut. So it's just all the way around here. Yeah, that would be the boundary of a sheet of paper. Then how about, let's take a look at, as a second example of a surface, how about a sheet of paper with a hole cut out of it. So I pre-cut out a hole out of a sheet of paper, and now the boundary consists of this outside edge out here, the four edges out here, but also this egg-shaped cut right there is another place you could get a paper cut. So the boundary of this surface consists of those two separate pieces, the four line segments on the outside and then this sort of circular or elliptical part on the inside. Let's take a look at also sort of the example of like a chopped cylinder. This is almost like a TP roll or something like this. So I just took a sheet of paper and I, taped it together so it just creates like a little bracelet like that. This surface here, here's another version. This is actually an empty TP roll. Same basic shape, right? And so here, the boundary of this surface consists of this circle on this side as well as that circle on that side. Those are the places you could get a paper cut. Let's also take a look at the example of a cheesecloth, or just any, towel or whatever that you have lying around. So here's mine. And so this is, of course, not made out of paper, but if it were made out of paper, this part right here on top is not going to cut me. It's the edge along here, right? The finished, the finishing of this sewing on the edges. That's the places to get a paper cut here. So this is really the shape of the boundary here would consist of four separate line segments. Let's take a look at the example of a soda bottle. Okay, so this is made out of plastic, sure, but if this were made out of paper, none of this part would ever give me a paper cut. The only place you'd get a paper cut would be right on that circle at the top where you drink from. Yeah, that the rim at the top. So for the soda bottle, the boundary is the boundary of the soda bottle is the rim at the top. Okay, so the place where you drink from. For a t-shirt, yeah, this is made out of cloth too. Oh, by the way, showing this shirt on screen, you can also see there's no shenanigans a little later in the video of like, is left and right switched or something. Everything looks the way it should. Like, if I were wearing this shirt in class, this looks correct to you in the video, yeah? So the boundary here would consist of this circle right there, and then this circle where one arm goes through, another circle on the other side where the other arm goes through, and then the circle at the very bottom from which you end up wearing the shirt. Let's also write down, so that's the shirt example, the t-shirt example, with its four holes, right there. So the boundary of the t-shirt consists of four holes. Sorry, not the holes themselves, but four circles. Okay, it's the sort of ribbing on a typical t-shirt. And then for two more purely mathematical examples, let's take a look at z is equal to root 1 minus x squared minus y squared. So this is the top half of a unit sphere. And so the boundary here is going to be a unit circle. Unit circle in the xy plane. And then as a last example, how about z is equal to root x squared plus y squared. Okay, so this shape on its own is a cone that goes on forever. So let's also include the restriction that z needs to be less than or equal to 5. Then by doing this, you have this cone, and it stops, right? And then the boundary in this case is this circle at the top. Yeah, so the boundary is the circle. Yeah, in this case, the boundary is a circle of radius 5 in in the plane, z is equal to 5. Now, here's the thing about all of these things. I use phrases like where you would get a paper cut to help clarify what the heck boundary is without giving a more formal definition. Now, if you are asked, say on a quiz or a test, here's a surface, find the boundary of it, you don't just want to parrot off this language of, oh, it's just where you get a paper cut. No, you've got to process that, right? Like if this object were described to you on a quiz or test, or just even for homework for that matter, you don't want to just say, oh, the boundary is where you get a paper cut. You want to say the boundary is this circle and this circle. You got to process where you get a paper cut on this thing. Now, that was talking about boundary. Now that we've talked about boundary, there's one other aspect of Stokes' theorem to clear up before we look at examples. That is, what do we mean by compatible orientation, or what do we mean by positive orientation? Well, at least in the special case of a simply connected surface or an object that has no holes, what you do is you place or rotate S so that the end vector, so that the orientation of the surface points directly towards you or at you. Then we should orient capital C, which we define to be the boundary of S, to be counterclockwise from your viewpoint. So let's take a look at this sheet of paper, right? So there are two possible, let me first rotate this so that it's not at you. So sort of this way, there's two possible orientations. There's this side and there's that side. And it doesn't really matter which we pick right now. Let's just go ahead and pick this side because I've got to just rotate a little less. And now this, this arrow is pointing at you, right? And so now that this is pointing at you, what you need to do here is travel in a counterclockwise fashion this way. To help try to clarify what is going on with that, I've got this vector here. So what I have is it's a just like a suction cup. I've super glued this to a barbecue skewer. I've just put a bit of Play-Doh at the top so that along the barbecue skewer and then the Play-Doh, the direction that that points, that's the orientation, that's the end vector. And then if I point this right at you, you'll notice that my hand is getting in the way of this. Let's see, let's try that. You can see over here, I've drawn in Sharpie on the suction cup itself, I've drawn a counterclockwise circular arrow shape. Yeah, I hope that's visible. Okay, and so if oriented this way on the sheet of paper, then you can, just move this, rotate this around to see that, the direction that this arrow points means we need to go travel this way for compatible orientation or positive orientation. Same thing with the cheesecloth. It's not really morally any different from a sheet of paper, right? So you take the cheesecloth and let's say you're going to orient this way, then we'll just move this arrow right along till we get to the edge where the boundary is, and you'll see that this piece of the edge we need to orient in that in this direction, not that direction. For another example, let's take a look at z is equal to root 1 minus x squared minus y squared, and let's take that, this is the top half of a circle, and let's say that we orient this upwards. So this, we need to specify this is oriented upwards, and then if we draw a quick picture, we're talking about like, okay, there's the equator and then there's the top of this, and if this is oriented upwards, that means all the arrows are like the upwards or outwards, and that means, if we can just imagine taking this thing here and imagine this, circular thing down at the bottom, that would look like this, yeah, each time. And so if we look from above, so our eye is here and we look down, we should end up seeing for the boundary circle, which is down here, if the orientation to be counterclockwise would need to look like that. If you want, you can draw, another one of, these little circular arrows, just draw them closer to the equator. And I think you can see that a little better there. Let's also look at an earlier example of z is equal to root x squared plus y squared with the additional restriction that z is less than or equal to 5. And let's say we orient this outwards, I guess is the right kind of terminology. So you've got this cone, and so you have like an orientation vector that goes this way, and so based on, what the arrow that was just drawn here is the end vector for orientation, and then now trying to draw the little sharpied arrow that's down here, it would go like that, yeah? And so then if we see, maybe I'll curl that, just rotate that a little more in the drawing. So we see that this boundary circle, we had already discussed where the boundary was, good thing we talked about that first, but that this should be oriented that way. So it's actually the reverse direction of the circle that we see there. And then let's just take a look at the example of a soda bottle. Okay, we had already discussed that the boundary should be up here at the top from where you drink from. That's where the paper cuts would occur. And then if we orient this outward, just because I practically speaking can't at least show you the orientation inward, but if we orient this outward, you'll see that, let me just slide this arrow right up there, and you see with the orientation arrow pointing towards you, this circle at the top, we're going to have to orient at least the point that's closest to the camera for you here, that needs to be oriented to the left.